Hello, everybody. Today we're focused on U substitution versus integration by parts. U substitution is fair game for both the AB and the BC exam, whereas integration by parts is solely on the BC exam. Without further ado, let's focus on first the key elements to be really strong at these, or the keys to success. First, it's crucial that you know the key formulas and processes for each method. You just got to know those cold. And then from there, it's important to know how to identify the appropriate method given any integral. Today we'll focus just on integration by parts and U substitution. And then once you know what the correct method is, it's important you know how to execute that method with indefinite integrals, and then also be able to apply it with definite integrals. You want to be able to do both indefinite and definite integrals. So the key formulas and processes for each method. First off, when do we use U substitution? We use U substitution when a form of the derivative of an inside function is hanging around in the integrand. We'll see a few examples of these on the next slide. Whereas integration by parts is very helpful when, in two cases, there's a product of two unrelated functions in the integrand, or we are asked to find the antiderivative for a function we don't know the antiderivative of. Then in terms of process for U substitution, we set U equal to the inside function. Then we differentiate U to get du, and then manipulate du equation to match the integrand, substitute, integrate, and resubstitute. In terms of integration by parts, our process is identify U using ilate. I'll define that acronym on the next page. Set dv equal to the rest of the integrand, differentiate U to get du, integrate dv to get v, and then finally apply the formula integral of uv equals uv minus integral v du. Couple note about integration by parts. I introduced this acronym on the previous page, ilate. I've seen many AP Calculus teachers use this to help teach integration by parts, and that is how you choose what U should be in the integration by parts formula. Here's what that acronym stands for. Inverse trig, logarithmic, algebraic, exponential, trigonometric. When you look at the integrand, you want to scan first, is there an inverse trig function? No. Is there a logarithmic function? No. Is there an algebraic function in that form? Yes. We're going to set U equal to that. Whichever one in the list you see first, that's what you should choose to set U to. This will work about 90% of the time. If you get stuck, just means it's one of those edge cases where it doesn't apply. Also for integration by parts, need to know your integration by parts formula, which is integral of U dv equals uv minus integral v du. You don't need to know the derivation for this for the AP exam, but it's important that you know the formula headed in so you can get a question like this correct. With that, moving on, we're going to shift to identifying the appropriate method focused on U substitution first. So in all four of these integrands, we're looking for a form of the derivative of an inside function to be hanging around in the integrand. In this first integral, I quickly see the inside function is x squared. It's inside the function sine of x. So what is the derivative of x squared? I know that is 2x, and I clearly see that hanging around on the right side, on the left of where it says sine of x. We see that right here. The derivative of this is hanging around. Let's look at the next one. Again, the inside function is x squared. And when we take the derivative of x squared, we actually get 2x. That is a form of 4x. We'll see that we can handle any coefficient here as long as it's constant, but x kind of looks like 2x, so we'll be able to make that work with U substitution. Third one looks a little bit different. Here is actually a composite function. We have e to the x with sine of x on the inside, so sine x is my inside function. And then I do see the derivative of sine, which is cosine, hanging around on the outside. The fourth one may look very much like it may be a long division or a partial fractions question. This is actually U sub. If we look at the denominator, that denominator is inside the function 1 over x. So it's like we had 1 over x and we substituted x to the fifth plus 6x. In the numerator, we see the derivative of that hanging around, this part here. So this numerator is the derivative of what's in the denominator right now, so we'll also be able to use U sub. All four of these can use u sub. And if you need extra practice, these are good ones to come back to. Shifting gears back to integration by parts. When do we use integration by parts? There's a product of two unrelated functions in the integrand, or we are asked to find the antiderivative for a function we don't know the antiderivative of. So when I look at these few examples here, we don't see a u substitution case. We don't have an inside function with its derivative hanging around. I have an algebraic function multiplied by a trigonometric function. That is the product of two unrelated functions. Then in the second integrand, we see a similar case. Still have 2x as the first function, but then natural log of x is our second function. In the next two cases, these match the second criteria. We're asked to find the antiderivative for a function we don't know the antiderivative of. If you have the antiderivative ln of x memorized, great. If you don't, you can always come back to integration by parts. We don't have the derivative natural log memorized, so this is a case where we can use integration by parts. Same thing goes for arctan of x. So the first two match that first criteria, second two match that second criteria. So now we've covered when to use each of these independently. Let's look at the next slide where we'll see 8 integrals and need to determine which ones are u sub and integration by parts. At this point, I want you to pause the video just to see if you can identify all of these independently. After you pause the video, I'll be able to break these down in a moment. All right, let's break each of these down. Hopefully you wrote them down on a note card or something like that. Here we go. First one's gonna be integration by parts. Just have 4x times cosine of x, that's it. I don't have any derivative of the inside hanging around, so that's integration by parts. Second one's a little bit different. We have that inside function of x squared, derivative of that is 2x, and a form of that, which is 4x, is hanging around on the outside. Next one, integration by parts, natural log of x, x squared, unrelated functions being multiplied. Fourth one, also integration by parts, exponential function e to the x, and 4x, separate functions, unrelated, being multiplied. Fifth case here is u substitution. We have 3x to the third plus 2 in the exponent of e to the x, so that 3x cubed plus 2 is an inside function, and we have the 5x hanging around in the front. We should, just a quick correction here, should have a dx here, and then also a dx here. Moving on to the sixth integral, this is also u substitution. Derivative of tan x, which is the inside function, is secant squared of x. So we're able to see derivative tangent is hanging around. That makes that u sub. Third case, integration by parts. No chance of u substitution, no derivative of an inside function hanging around. And hopefully you got the last one as well. That is integration by parts. 9x is totally separate from arc sine of x dx. All right, so now that we've capped off when to use each method, now we're going to shift to how do you actually implement these methods for indefinite integrals and also for definite integrals. Starting with indefinite integrals, I'm going to have our process here on the left. I have some completed sample work here that you can pause the video and check out. I'm also going to switch to my DocCam and model this one live so you can see it in motion along with my thinking out loud. Adjust whatever works best for you to help you master this. All right, so I had the same integral from the screen earlier, and my first key step is to set u to the inside function. So I'm going to do that. I'm going to kind of do my scratch work over here, and then I'll come back over here to do any manipulation of the integral. So over here, I'm going to say u equals that inside function. That is 10x cubed plus 5. Second step is differentiate u to get du. I have my u equation. I'm going to take the derivative of that to get du, and I get 30x squared dx. Just like that. Third step is we need to manipulate this equation here to match what's hanging around here. So I see an x squared and a dx. I have that 5, so I'm going to just ignore that 5 for now and then change the right side of this equation to match that x squared. So I'm going to divide both sides by 30. I get du over 30 equals x squared dx, just like that. So far we've chosen u, differentiated du, and then we've isolated x squared dx to match what we have over here. Now, we're going to take that original integral, we're going to keep the integrand sign, and we're going to keep anything I don't plan to substitute out. So I'm going to keep that 5 there. I'm also going to keep the cosine, like this. And then my two substitutions, first I'm going to substitute u for 10x cubed plus 5. So where I saw the 10x cubed plus 5, I'm replacing that with u, just like that. Then I also saw there's an x squared and a dx. So I'm going to substitute this and this out of the integrand and substitute du over 30 in. So I write that here, du over 30, just like that. So now I'm going to manipulate some things just to simplify, not a formal step, just simplifying some things. 5 over 30 is 1 over 6. And then I have cosine of u du. So I've completed my substitution. Once I've done that, I need to integrate. The whole purpose of this is to take the antiderivative. So make sure you take the antiderivative before you go back to x. With that, when I take the antiderivative of this, I get 1, 6, keep my coefficient. Antiderivative cosine of u is sine of u plus c. And right now my answer is in terms of u. I need that to be in terms of x. So I use my u equation here, replace u with 10x cubed plus 5. 1 over 6 sine of 10x cubed plus 5, close parentheses, plus c. And we've completed that u substitution question. Coming back to the PowerPoint. We just got that same answer, 1/6 sine of 10x cubed plus 5 plus c. That is your first question today on u substitution applied to indefinite integrals. Now let's shift gears. That's our process. Now let's shift gears to integration by parts, focusing on this process here. I'm going to switch back to the DocCam. If you need to pause the video just to preview the work, that is fine. And let's take a look at this one on paper. Integration by parts, indefinite integral. So first step I have is to identify u using I late. I'm just going to write that at the top here as an acronym for me to think about. When I scan through this integral, I don't see an inverse trig. I'm going to cross that out. When I scan through this integral, I don't see a logarithmic function. I'm going to cross that out. When I scan through this function, I do see 5x. So I'm going to set u equal to that algebraic function. So u equals 5x, just like that. Then my second step is to set dv equal to the rest of the integrand. This part was u, everything else is going to be dv. So I write dv equals cosine of x dx, just like that. Next step is to differentiate u to get du. Du equals 5 dx, just like this. And then we also want to integrate dv to get back to v. So v, antiderivative cosine, is sine x, just like that. So now that we've done all this, this part of the toolbox, now we just apply that formula. For reference, in the moment, I'm going to just write out that formula. It is integral of u dv minus, or equals uv minus integral v du, just like that. And the key to this formula is that this part has already been given to you, and then we want to use this equation to rewrite that integral in another form. So watch carefully for how we do that. We've already identified u in all those pieces, so now we know exactly what to plug in over here. U is equal to 5x. V is equal to sine x minus, this is a v, just to clarify, the integral of v, which is sine x, and then du, which we have 5x, or just 5, apologies, 5 dx, just like that. Then from there, we're going to simplify some things just to make this a little bit easier to work with. Minus integral of 5 sine x dx. Here, this 5 sine x is just going to stay 5x sine x. And then when I take the antiderivative of 5 sine x, that's going to be negative cosine x. So when I do that, it's going to be a negative from the integral. Then I have this leading negative. That's going to be plus 5 cosine of x plus c. And there we go. We have solved an indefinite integral using integration by parts. Take a moment to rewind, replay any of those quick steps if you got stuck. And let's move back to the PowerPoint for 2 more questions. All right, so now we're going to look at definite integrals. Using that same process, what I want you to look very carefully for is how we use that same process we just saw with indefinite integrals for definite integrals. We're going to kind of do some indefinite work on the side and then bring it back to the definite integral. So here's the work on the right if you want to preview that. I'm going to take it live on the .cam now. So use substitution with definite integrals. What makes this a definite integral, remember, is that I have my limits here. In the previous 2 cases, we did not have those limits. So without further ado, let's dive into this question. So I know whenever I have an indefinite integral, my big steps are to take the antiderivative of whatever's here and then plug in the upper, plug in the lower, and subtract them. That's our evaluation theorem. What I'm going to do instead for this question is I'm going to do some scratch work here to just find out what is the antiderivative of this. And then we'll take that and then use those limits in whatever that antiderivative is. So we're really going to kind of do some scratch work here to find what is the antiderivative of this, if it was like as if it was an indefinite integral. And then we'll just apply those limits. We'll see how that breaks down in a second. So it's u substitution. U, remember, is that inside function. U equals 2x squared plus 1. We differentiate u to get du. We get 4x dx. Now here's a point where you can make use some math finesse to make this a little bit simpler. When I look at the integrand here, I just have 4x. That already matches this part, so I can skip that extra manipulation step because it already matches that part in the integrand. So now, if I think about this just as an indefinite integral, 4x e to the 2x squared plus 1 dx, when I perform my substitution, I'm going to replace the exponent with u, so I get e to the u, just replace this piece here. And then instead of just replacing the x and the dx, I'm going to replace the 4x and the dx. And when I do that, I'm just going to replace it with du. So I get du just like that. Still need to take the antiderivative. When we take the antiderivative of that, we do get just e to the u plus c. Then I want to go back to x. So it'll be e to the 2x squared plus 1. Remember, I got that from up here. And don't forget your plus c. Okay, so with that, now I know this is the antiderivative of this function. So I know the antiderivative of this function is e to the 2x squared plus 1 evaluated from 0 to 1. And then from there, we just plug in our limits. When I plug in or substitute the upper limit, I get e to the 2 times 1 squared, that's 2 plus 1, that's 3, minus e. If I plug in substitute 0 for that exponent, I get 0 plus 1, that is 1. And my answer is e cubed over e to the 1. So now we've done an indefinite integral and a definite integral with u substitution, so you know how to handle those limits moving forward. Take a moment to rewind the video if you need to check any of those out. All right, so moving on to our final part of this lesson is executing integration by parts for definite integrals. We don't often cover this, it doesn't often come up on the AP exam, but we want to be prepared for everything. So let's dive into this one. Feel free to pause the video to preview the work before we take it live. All right, final question. Here we go. Integration by parts, definite integrals. So similar to the last question, we're going to just ignore these limits while we take the antiderivative. And then we'll apply those using the antiderivative momentarily. So integration by parts, I'm thinking I-L-A-T-E. I'm going to pick what U is first. I-L-A-T-E. Scanning the integrand, is there any inverse trig? No, I don't see any. Scanning the integrand, do I see any logarithms? Oh, I do. So I'm going to choose L for my U. So I get ln of x just like that. Then remember we set dv equal to the rest of the integrand. So dv will be 4x natural log, or not natural log, just dx here. Apologies. And then from there, we differentiate u to get du equals 1 over x dx like this. And then v is the antiderivative of dv, which would be 2x squared, just like that. So now it's important that we apply the formula. When I have that memorized, so watch carefully for how we do this piece. We start with 4x ln of x dx. And then we're going to use that formula to convert this to an integral that's easier to solve. So with that, we have ln of x times 2x squared, that's my uv, minus integral v 2x squared du, which is 1 over x dx. So that's just our use of the formula for integration by parts. From there, we're going to simplify. This would be 2x squared natural log of x minus, when I think about this next part, 2x squared divided by x, that's really just 2x when I simplify that. And then from there, keep this first part, 2x squared ln of x, minus antiderivative of 2x, that is x squared, and I put my plus c. So now, very similar to the use substitution question we saw a moment ago, we are going to take this definite integral. We just found the antiderivative, and so we're going to write that antiderivative in brackets. Drop the c because it's a definite integral. And now we just need to substitute and solve. So I substitute my upper limit. This will equal, move this down a little bit. This will equal 2 times 2 squared. That's going to be 2 times, that's going to be, sorry, 8. Then natural log of 2 minus, and then we substitute 2, we get 4 here. So that's just the upper limit substituted. Then we have 1 substitute for 2, natural log of 1, we're just going to write that out so we can see it, minus 1 squared, which is just 1. Didn't need to write all that. Then from there we get 8 natural log of 2. I look at the natural log term here. This is actually 0. Natural log of 1 is 0. And then we have this minus 4 minus a negative 1. So minus 4 plus 1, that's negative 3. And our answer is 8 natural log of 2 minus 3. Pause and rewind if you need to recap any of that. Flipping back to the PowerPoint now. All right, while I was working through that example, I caught a quick typo here I'm going to correct on the slide. As you saw in the example we just completed, this should be 8 natural log of 2. I made a mistake here, and so this should be 8 natural log of 2 when you substitute 2 here. So just make sure you make that adjustment with your own work. And with that, let's rewind the slides. And bring it back to our keys. It's important to know those key formulas processes for each method. Then important to identify the appropriate method. And if you have those 2 things down, you just got to make sure you can execute this with indefinite and definite integrals. Hope you found this video helpful in mastering integration by parts and use substitution. Next video is going to most likely focus on long division versus partial fractions. I appreciate any feedback that you have so I can make these videos better in the future. Thank you.